Windows Auto Proxy Detection Overview. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Windows Auto Proxy Detection is a feature designed to simplify network configuration in enterprise environments by automatically discovering and applying proxy settings without requiring manual user configuration. When you enable the Automatically Detect Settings option in Windows Internet Options, the operating system implements a sophisticated discovery mechanism called Web Proxy Auto Discovery Protocol, commonly abbreviated as WPAD. This protocol attempts to locate a proxy configuration file that contains JavaScript instructions telling the system which proxy server to use for different destinations. The fundamental security problem with WPAD is its reliance on multiple fallback discovery mechanisms that were designed for convenience rather than security. When Windows searches for the WPAD configuration file, it does not just check one location and then stops. Instead, it implements a cascading sequence of discovery methods, each progressively less secure than the last. This cascade includes DHCP option 252, DNS queries for wpad.domain.com, and even NetBIOS name resolution in some configurations. The system will try each method in sequence until it successfully retrieves a configuration file, and this is where the critical vulnerability lies. The most dangerous aspect of WPAD is that it operates transparently to the user. When you open your web browser or any application that respects system proxy settings, Windows silently performs the WPAD discovery process in the background. If an attacker can position themselves to respond to any of these discovery queries before the legitimate proxy server does, they can provide a malicious proxy configuration that redirects all of your traffic through their controlled infrastructure. This is not a theoretical vulnerability requiring sophisticated exploitation techniques. It's a design characteristic that attackers can abuse with relatively simple tools. Understanding WPAD exploitation requires examining the protocol stack from the bottom up. At the network layer, WPAD relies on DNS, DHCP, and in some cases, NetBIOS and LLMNR for name resolution. At the application layer, it retrieves a PAC file, which is actually executable JavaScript code that runs with system privileges to determine routing decisions for every network connection. An attacker who can compromise any layer of this stack can potentially intercept, modify, or redirect all HTTP and HTTPS traffic from the victim machine. This makes WPAD attacks particularly attractive to threat actors because successful exploitation provides comprehensive network visibility and control. WPAD discovery mechanisms. The Web Proxy Auto Discovery Protocol implements multiple discovery mechanisms organized in a specific priority order. Understanding this cascade is essential because each method presents different attack surfaces and exploitation opportunities. Windows attempts these methods sequentially. The first successful response wins, regardless of whether that response comes from a legitimate server or an attacker. This first success model is fundamentally insecure in untrusted network environments. The first discovery method Windows attempts is DHCP option 252. When your computer obtains an IP address from a DHCP server, the server can include numerous optional parameters in the DHCP response. Option 252 is specifically designated for WPAD and contains a URL pointing to the PAC file location. In a properly configured enterprise network, this is the most secure WPAD method because the DHCP server is typically under administrative control and protected from unauthorized access. However, in practice, many networks do not configure option 252, causing Windows to fall through to less secure methods. When DHCP option 252 is not present, Windows proceeds to DNS-based WPAD discovery. This method constructs DNS queries by prepending WPAD to the system's DNS suffix search list. For example, if your computer is configured with the domain corp.example.com, Windows will query for wpad.corp.example.com. If that fails, it removes the leftmost subdomain and tries wpad.example.com, then wpad.com. This iterative process continues until either a successful DNS response is received, or the search list is exhausted. The security vulnerability here is evident. If an attacker controls DNS resolution at any point in this chain, they can provide a malicious response. The DNS WPAD attack is particularly dangerous when the search climbs up to public top-level domains. There have been documented cases where researchers registered domains like wpad.com or wpad.co.uk and observed thousands of computers from around the world automatically sending WPAD discovery requests to these domains. This happens when corporate networks have misconfigured DNS suffix search lists that eventually resolve to public domains, or when employees connect their corporate laptops to untrusted networks like coffee shop Wi-Fi while still having the auto-detect setting enabled. In older Windows versions or specific configurations, the discovery cascade includes even more problematic protocols like LLMNR and NetBIOS name resolution. Link Local Multicast Name Resolution is a protocol that broadcasts name resolution queries on the local network segment when DNS fails. NetBIOS name service operates similarly. Both protocols are completely unauthenticated and trivially spoofable. An attacker on the same network segment can listen for these broadcast queries and respond faster than any legitimate server, a technique called race condition exploitation or name poisoning. Tools like Responder automate this entire attack process, making it accessible to even unsophisticated attackers. PAC file exploitation. The proxy auto-configuration file, universally referred to as a PAC file, is the payload delivered through WPAD discovery. Understanding PAC files is crucial because they represent the actual mechanism through which attackers gain control over network traffic. A PAC file is not a simple configuration file with static proxy addresses. It is executable JavaScript code that runs every time any application needs to determine how to route a network connection. This design provides tremendous flexibility for legitimate network administrators but also creates an enormous attack surface when that code comes from an untrusted source. A PAC file must contain at least one JavaScript function called findProxy for URL, which accepts two parameters: the URL being accessed and the hostname extracted from that URL. This function executes synchronously for every single HTTP or HTTPS connection attempt, and its return value determines exactly how that connection will be routed. The function can return direct to indicate the connection should bypass the proxy hostname port to route through a specific proxy server, or SOCKS hostname port to use a SOCKS proxy. It can also return multiple options separated by semicolons, providing fallback mechanisms. The security implication of executing JavaScript for every connection is profound. The PAC file has access to a rich set of JavaScript functions specifically designed for network decision-making. These include functions to check if an IP address is in a specific subnet, to resolve host names to IP addresses, to check if the current date falls within a specific range, and to perform string matching operations. While these functions are intended for sophisticated routing logic, they also enable attackers to implement conditional exploitation based on the victim's environment, the websites being accessed, or temporal factors. A typical malicious PAC file implements a man-in-the-middle attack by routing all traffic through an attacker-controlled proxy server. The simplest malicious PAC file might contain just a few lines of JavaScript that always return the attacker's proxy address regardless of the destination. More sophisticated attackers implement selective interception, where sensitive traffic like banking sites or corporate resources is redirected while normal browsing goes direct, making the attack less noticeable to the victim. Some advanced PAC exploits even include logic to detect security tools or analysis environments and behave benignly when under scrutiny. Once traffic is routed through an attacker's proxy, they have complete visibility into all HTTP traffic, including URLs, headers, cookies, and post data. For HTTPS traffic, the attacker sees the destination hostname due to server name indication in the TLS handshake, and they can attempt secure sockets layer stripping attacks or present fraudulent certificates. If the victim has installed a corporate root certificate, common in managed environments, the attacker can perform perfect secure sockets layer interception by presenting certificates signed by that trusted root. Even without secure sockets layer interception, the attacker gains valuable intelligence about the victim's browsing patterns, corporate resources being accessed, and can inject malicious content into any unencrypted HTTP responses. Attack scenarios and exploitation. Real-world WPAD exploitation occurs across multiple threat scenarios, each with different attacker capabilities and victim profiles. Understanding these scenarios helps security professionals assess their actual risk exposure and prioritize defensive measures appropriately. The common thread across all scenarios is the automatic, silent nature of WPAD that makes attacks nearly invisible to victims until significant damage has occurred. The most prevalent attack scenario is the corporate network insider threat or the coffee shop evil twin attack. In this scenario, an attacker either gains physical access to a corporate network segment or sets up a rogue wireless access point that mimics a legitimate public Wi-Fi network. When victims connect to this network, their Windows computers immediately begin WPAD discovery. The attacker runs tools like Responder or similar frameworks that monitor for DHCP requests, DNS queries, and LLMNR broadcasts related to WPAD. As soon as they observe a WPAD query, they respond with a malicious pack file hosted on their local web server. The victim's computer accepts this pack file because the WPAD protocol has no built-in authentication or integrity verification mechanism. The computer immediately begins routing traffic according to the malicious JavaScript instructions, typically sending everything through the attacker's proxy. From the victim's perspective, nothing appears wrong. Websites load normally, applications function correctly, and there are no warning messages or error dialogues. Meanwhile, the attacker is logging every HTTP request, capturing authentication credentials transmitted over unencrypted connections, and potentially injecting malicious payloads into HTTP responses. A more sophisticated attack scenario involves DNS hijacking or compromised DNS servers. In this case, the attacker does not need to be on the same network segment as the victim. Instead, they compromise or control a DNS server that the victim uses for name resolution. This could be the victim's home router running a vulnerable firmware, a compromised corporate DNS server, or a malicious DNS server provided by a hostile network. When the victim's computer performs WPAD discovery and queries for wpad.domain.com, the compromised DNS server responds with the IP address of an attacker-controlled web server hosting a malicious pack file. The DNS hijacking attack is particularly insidious because it can persist across network changes. If the victim's laptop is configured to use a specific DNS server, perhaps through a VPN configuration or manual setting, the attack continues even when the victim moves to different physical networks. Additionally, DNS responses can be cached by the operating system and by intermediate DNS resolvers, meaning a single malicious DNS response can affect the victim for an extended period, potentially hours or days depending on the TTL value set by the attacker. Enterprise environments face a unique risk from WPAD called the WPAD domain registration attack. This attack exploits misconfigured DNS suffix search lists in corporate environments. If a company uses the domain corp.example.com but hasn't properly configured their search list, employee computers might search for wpad.corp.example.com, then wpad.example.com, and potentially even wpad.com. If an attacker registers one of these higher-level domains, they can provide malicious pack files to thousands of corporate computers simultaneously. This attack was demonstrated at scale when security researchers registered wpad.com and observed massive amounts of corporate traffic attempting WPAD discovery against their domain. Defense and mitigation strategies. Defending against WPAD-based attacks requires a multi-layered approach that addresses both the protocol-level vulnerabilities and the organizational policies surrounding proxy configuration. The most effective defense is also the simplest: disable automatic proxy detection entirely. In Windows, this is accomplished by unchecking the Automatically Detect Settings option in Internet Options. For enterprise environments, this setting can be enforced through group policy, preventing individual users from enabling it. However, disabling auto detection requires having an alternative proxy configuration method in place, which brings its own management overhead. For organizations that genuinely need automatic proxy configuration, the most secure way to implement WPAD is through DHCP option 252. By providing the PAC file URL through DHCP, you eliminate the insecure DNS-based discovery and the even more dangerous LLMNR and NetBIOS fallback methods. The DHCP server should be hardened against unauthorized access, and DHCP snooping should be enabled on network switches to prevent rogue DHCP servers from operating on the network. Additionally, the PAC file itself should be hosted on HTTPS URLs with valid certificates, providing both authentication of the source and integrity protection for the content. DNS security is critical for WPAD defense even when using DHCP option 252, because users might configure devices outside the managed environment or the DHCP method might fail for various reasons. Organizations should ensure they own and control all potential WPAD domains in their DNS hierarchy. This means registering wpad.yourdomain.com and ensuring it either points to a legitimate PAC file server or returns NXDOMAIN to prevent attackers from taking advantage of failed lookups. DNS suffix search lists should be carefully configured to never climb to public domains, and DNS-SEC should be implemented to prevent DNS spoofing attacks. Network segmentation and monitoring provide defense in depth against WPAD attacks. Critical systems should be isolated on network segments where LLMNR and NetBIOS are completely blocked at the switch level. Network monitoring should include alerts for suspicious DNS queries related to WPAD, particularly queries that resolve to external or unexpected IP addresses. Proxy logs should be analyzed for unusual patterns like sudden changes in proxy configuration sources or traffic routing through unexpected proxy servers. Endpoint detection and response tools can monitor for malicious PAC file downloads and unexpected proxy configuration changes. User education, while often considered the weakest layer of defense, plays an important role in WPAD security. Users should be trained to recognize that connecting corporate devices to untrusted networks, such as public Wi-Fi, carries significant risk. They should use VPN connections that bypass local proxy discovery. IT policies should clearly define when and where automatic proxy detection is appropriate, and provide users with secure manual proxy configuration information for use in untrusted environments. Regular security awareness training should include examples of WPAD attacks and their consequences to help users understand why these policies exist. Thank you for your attendance. Please consider subscribing to the channel and liking this video.